Okay, so we are doing the Chapter 4 review. So without further ado, let's jump into it and see what we can get done. So of course, we have our vocab words. This is our first unit that really is heavy on the calculations. So make sure you know what each of these words mean. Now, let's look at number 1. It says, which of the statistics is defined as the 50th percentile? So the 50th percentile is the same as Q2, the second quartile, which is also known as the median. So let's look here. Is it the mean? No. Is it the median? We just said it. So, I mean, that goes back to knowing vocab. I mean, that's all that boils down to. Know your vocab. Okay, number 2, each value in a sample has been transformed by multiplying by 3 and then adding 10. If the original sample had a variance of 4, what is the variance of the transformed sample? Okay, so what I want to do here is type a note, because this type of problem is not characteristic of this chapter. So let's type a note here. Control B. Note. This is more of a random variable type of problem. Meaning, when we cover random variables, we'll cover it. So by the end of this semester, we'll have it covered. However, we can use the following formula. So the variance of x, ax plus b is equal to a squared times the variance of x. Okay, so let's make that bold and red and put that up here. So let's see. Let's see what we can muster up here. Okay, so using that formula, it says the variable, so let's call the new variable y. New variable y is equal to 3 times x plus 10. So the variance of y is equal to the variance of 3x plus 10, which really is just 3 squared times the variance of x. Well, what is the variance of x? What did they tell us? It had a variance of 4. So we can do 3 squared is 9 times 4 gives you 36. So even though we haven't covered it, the answer is E. Now, This won't be on the test. So let me add that. So we haven't covered this. This type of problem will not be on the test. But let's calculate it. Gives us, so chapter 7 is when we'll really get to do this stuff. Then it will be covered and you will be expected to know it. But for now, it's just like, here's a little extra. Okay, number 3. The graph, or a graph, that's not shown of the selling process of homes in a certain city for the month of April reveals that the distribution is skewed to the left. Okay, skewed to the left. So that means our tail is on the left. So it probably looks something like this. Or we've got a long tail over here. Which of the following statements is the most reasonable conclusion about the selling prices based on the graph? Well, there's our graph. So if we go through each of these, let's talk through them. A, the mean is greater than the median. This would definitely be false. Because for left skew data, the mean is less than the median. B, the median is the average of the first quartile and the third quartile. Not necessarily. Think of our box plots. If that was the case, the median would always be in the middle between the first and third quartile. Is the median always exactly in the middle? No. So for this one, we're going to say not necessarily. C, there are fewer selling processes between the first quartile and the median than there are between the median and the third quartile. No. Median goes by number. So there's not going to be fewer selling processes. The median is where half are below, half are above. First quartile, if you look at just, this is just false. So false. There are more selling prices that are less than the mean than selling prices that are greater than the mean. Well, again, this would be false. I'm going to say C, comment on A. Because it's false for the same exact reason that A is false. The mean is less than the median. So that means there's going to be more prices above the mean than there would be more prices above the mean than below the mean. E, the maximum or the value of the maximum minus the third quartile is less than the value of the first quartile minus the minimum. That's true. Because think of it, our maximum would be right here. Chances are, and of course, here's our minimum. So max, min. Our median is probably going to be right here, median. So the third quartile could be right about there maybe. So, and then the first quartile may be right there. So Q1, Q3. It's probably going to look something like that. The value of the max minus the third is less than the value of the first minus the min. Yeah, that's true. So that makes E our answer. Okay, number 4. Each person in a random sample of adults was asked how many DVDs he or she owned. Summary statistics are given below. Which of the following statements is true? Okay, so let's go through each of the statements and see which one is true. A says that 75% of the adults in the sample own more than 95 DVDs. Q3 is 95. So it wouldn't be 75% of the adults in the sample own more than 95. It would be own less than 95. So A is out. 50% of the adults in the sample own between 0 and 129.4. Remember, 50%, we want to look at the median. The median is equal to the 50th percentile. So I'm going to look at the median. The median says 50. So this should be a 50. C, the distribution of the number of DVDs owned appears to be approximately symmetric. Let's come back to that one. D, the interquartile range of the number of DVDs owned is 65. So remember, IQR is Q3 minus Q1, which is 95 minus 30, which is 65. Yeah, that's true. E, the distribution of the number of DVDs owned contains outliers on both the low side and the high side. Well, let's see, does it? Certainly the high side, yes. But would 0 be considered an outlier? No. 0 would not be considered an outlier. And let's see why. let's actually calculate what the outliers would be. So if I did Q1 minus 1.5, Q1 minus 3, IQR, sorry. IQR. Okay. So we said the IQR is 65. So Q1 is 30 minus 1.5 times 65. Remember, this value that we're getting right here would be the very first outlier. If it's smaller than this number, then it's an outlier. So 30 times 1.5 minus 65. Sorry, 30 minus 1, yeah, 1.5 times 65. That would be negative 67.5. Now, what's our minimum? Our minimum is 0. So do we have an outlier on the low side? No, we don't get anywhere close. So that one's out. So far we've eliminated A, B, and E. Now let's go back and look at C. The distribution of the number of DVDs owned appears to be approximately symmetric. Look at this. So the minimum is 0, Q1 is 30, median is 50, Q3 is 95, and then boom, we're out here at 3,000. Is that symmetric? If the middle's at 50, but then you have an end at 0 on one side and an end at 3,000 on the other? No, I don't think so. So no, it's not symmetric. The only one that's vetted and true is D. So D is our only true statement. Okay, number 5. Professor James gave the same test to his 3 sections of statistics students. On the 35-question test, the highest score was a 32 and the lowest was a 15. Based on the information displayed in the box plots above, which of the following is true? A, says section 1 has the smallest interquartile range. Remember, the interquartile ranges are the bounds on the box. That's the easiest way to explain it. So does section 1 have the smallest interquartile, or does section 1 have the smallest box? No. Section 2 has the smallest IQR. So that one's out. The lowest score in section 2 is higher than the highest score in any of the other sections. Section 2, buddy, is right here. It's our lowest score, period. This is our lowest, period, of all. So yeah, no. ain't gonna cut it. Section 2 has the smallest range of scores. Again, Section 2 has the largest range. So it's the lowest, it's got the lowest score and it has the highest score. So no, it's got the largest range. D, the top 25% of scores in Section 2 are lower than the highest score in Section 3. The top 25% in Section 2 are lower than the highest score in Section 3. The highest score in Section 3 is right here. Go up. No, they're not lower. They're higher. Not lower. Higher. So those can't be it. That one can't be it. I hope it's E because we've thrown out the rest of them. E, at least 50% of the scores in Section 3 are higher than all of the scores in Section 1. Well, let's look at this one. Where's the 50% mark on Section 3? It's at our median. Yeah, the median in 3 is higher than everybody in Section 1. So, yep, this is our answer. That's our answer. Okay, that's number 5. Number 6. The number of hurricanes reaching the east coast of the U.S. was recorded for each of the last 10 decades by the National Hurricane Center. The summary measures are shown below. So they give us the min, the max, the lower quartile, which remember this is Q1, the upper quartile, which is Q3, the median is 16 and is 10. Which of the following is a true statement? A, the smallest outlier is 12, and it is an outlier. No other observations in the data set could be outliers. Well, let's do this. Let's do this. Let's draw 10 blanks down here because there's only 10 observations. So let's try to visualize where everything's at. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so the min we know is 12. The max we know is 24. Here is going to be the median. Which is 16. This is going to be Q3, which is 18. This one's going to be Q1, which is 15. Okay, so our first outlier would be at Q1 minus 1.5 IQR. That would be the first outlier. Q1 is 15 minus 1.5. What's our IQR? The IQR is 3. So 15 minus 1.5 times 3 gives us, let's see, 10.5. So do I have an outlier on the low side? No. Let's make note of that. No outliers. Below, at least. Okay, now let's do the upper side to see if I'm going to have an outlier here. So Q3 plus 1.5 IQR. It's going to be 18 plus 1.5 times 3. $22.5. Ooh, so somewhere in here, yes, there is an outlier because 22.5, let's just say it's right there. I don't know where, but we could have an outlier. Now let's do Q3 plus, let's go even bigger than just that one. So plus 3 IQR. That's going to be 18 plus 3 times 3, which is 27. So we don't have any extreme outliers, but we do have a mild outlier above. So no extreme, but we do have a mild outlier. Okay, now let's look at our answer choices. The smallest observation is 12, and it is an outlier. No, 12 is not an outlier. B, the largest observation is 24, and it is an outlier. Maybe. Or yes, it is. Sorry. Yes, it is. 24 is greater than 22.5, so yes, it is an outlier. No other observations in the data set could be outliers. I don't know. It could be. I mean, that yes, the observation is 24, but this one could be 23 or 24. So no other observations? No, that part's wrong. Both 12 and 24 are outliers. No, 12 is not an outlier. 12 is an outlier. No, 12 is not an outlier. 24 is an outlier, and it is possible that there are other outliers at the high end of the data set. There are no outliers at the low end. Yes, that is true. We just said If this 9th observation is 23 or 24, then there would be one more outlier. But there's nothing at the low end. So, okay. So we've done that one about as much justice as we can possibly do. So E is your answer. Seven. Heights in inches for the 200 graduating seniors from Washington High School are summarized in the frequency table below. Which of the following statements about the median height is true? Okay. So we have 200 graduating seniors. That means that if we want to get the median, we have to look between, because there's going to be, we can divide it in half, the lower 100 and the upper 100. So look for the 100th and 101st observations. I just divided it in half. Okay, let's see. I'm going to do a running total. I'm going to do the cumulative frequency over here. That's going to be 22. 22 plus 84. It's going to be 106. I'm already past 100. So that means my median has to fall in this range. So which of the following about the median is true? It's greater than or equal to 60 inches, but less than 66. We're done. So the key here was to use cumulative frequency to find the 100th and 101st observations. And it's like, it's going to be in there somewhere. Well, we have 106 after just the second option. So that means it's got to be in that one somewhere. Can't be in the first one, can't be less than 60. But it can be in that second one. Okay, so now for number 8. Okay, so for this next one, we actually get our first workout question. So they give us this information about, looks like subway stops in New York. And that's great and everything. They're trying to improve how much space they have and all that good stuff. The bulk of this problem, though, deals with calculations. So they want us to calculate the sample mean and standard deviation of the space per standing passenger for morning rushes of 1987 versus the morning rushes of 1988. Now, on your version of the review, you don't have these tables in here. That's because I expect y'all to make them. We need to use the same methods that we used in class on how to calculate mean and standard deviation. So I expect you to make these tables. I put them in here so that way as we're going through it, you can see what the values you should be getting actually are. and I can help walk you through it. So what we need to do is first we need to get our mean. We need to get the sample mean. So to do that, I need to take the sum down here of each of these. So I'm going to do that. I'm going to go through and add up 3.2 plus 3.1 plus 2.9, etc. And so I'm going to use the sum. I'm just going to write the word sum down here, but then know that the summation symbol is sigma, capital sigma. So I'm going to get that for each morning, each of the mornings. I'm going to go through and get that right quick. So if I go through and I add them all up for the morning of 1987, you should get 61.5. And for 1988, you should get 59.2. Now, how many observations do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So that means for 1987, X bar would be equal to the sum of our x's divided by n, which is 61.5 divided by 19, which gets us approximately 3.24 square feet. Now, let's do 1988. 1988, we need to get the mean. So X bar equals the sum of my x's divided by n. So 59.2 divided by 19, which will give us 3.12 square feet. Okay, so there's our means for each of them. Now, what I want to do is go through and start working on getting my standard deviation. Well, to do that, I need to take the difference in the value and the mean. For instance, for the morning of 1987, I'll do 3.2 minus 3.24, which gives me, let me do it this way. Yeah, I'll just leave that. 3.2 minus 3.24 equals negative 0.04. See if I can make this wider. There we go. I'm going to go through and do this call. Oh no, let's do each of them. So now I have this negative 0.04. Now I need to square that. So negative 0.04 squared is equal to 0.0016. Let's see here. There we go. Undo that. Really? Okay, so then I'd go on to the next one. 3.1 minus 3.24 equals. Well, again, we're going to be negative 0.14. Okay, so there's that one. Now let's square it. Negative 0.14 squared equals 0.0196. Then we go to the next one. 2.9 minus 3.24 equals negative 0.34. Then I square that. .1156. And I'm going to just keep doing this all the way down until I get everything filled in. Okay, so I have everything filled in now. So hopefully you paused the video and checked everything, did your own, and then now you can check your numbers, see how you did. But here's our whole table filled in. Now we're ready to go for the standard deviation. So for that, remember that's S equals, and then we're going to have a big old square root, and it's going to be the sum of your x minus x bars squared. And this is sample standard deviation, so divide it by n minus 1. Well, let's add up this whole column here. I need to add up this left column, or sorry, this right column of my first table. If I add everything up on it, if I add everything up, I will end up getting 40.3044. Okay, so plug that in. That's going to be here, 40.3044. We already said n is 19, so 19 minus 1. Let's take the square root of that. That's going to get us to 4 decimal places, 1.4964 square feet. Remember, standard deviation is in the same units as your mean and as your data. So there's our standard deviation. Okay, so there's the values that we need for, whoa, I'm erasing stuff now. There's the values that we need for 1987. Now we're going to need to do the same exact thing for 1988. But this time our mean is 3.12. So I'm going to highlight our answers here. For 1987, the mean is 3.24 square feet. Standard deviation is 1.4964. Then we need 1988. Our mean is 0.312 square feet. And we have yet to calculate the standard deviation. So let's do it. Okay, so we need to do 2.8 minus 3.12. And that would get us, well, let's see. That would get us negative 0.32. Then we have to go and square that. So negative 0.32 squared would give us 0.1024. Okay, so there's that one. Let's adjust our columns here. Make sure our whole table stays centered. Okay, so there's our first one done. Now let's do the next one. So 2.0 minus 3.12 equals negative 1.12. Then we have to square that. And that would get us 1.2544. And then we do the next one. 2.9 minus 3.12. That's going to give us negative 0.22. Then we've got to square it. That'll get us 0.0484. And then we keep going until we get this whole table filled in. Okay, so now this one is all filled in. So we've got all the calculations done. Now, I'll say all of them. We have all of the tabular calculations done. So we've got to do the same process that we did for 1987. I need to add up this last column. When I do that, that'll give me 50, oh, let's write in pen, not highlighter. That'll get me 53.1056. Okay, so now it's time for our formula. So standard deviation is the square root of the sum of x minus x bar squared divided by n minus 1. So we take the square root. We're going to get that sum is 53.1056. Again, we have 19 observations, so 19 minus 1. You do that, and to 4 decimal places, you get 1.7176, and we need to do it in square feet again. Okay, so there's our standard deviation for 1988. So lots of calculation, but we made it. We got through this example. So now part B asks us to use our values in part A to describe the differences and similarities in the distributions of the morning standing room for the 2 years. Okay, well, let's see. Differences and similarities. Well, if we look at the square footage, they're pretty similar. So yeah, they were trying to increase square footage. They actually decreased it just a little, but they're pretty similar. But notice how the standard deviations changed. The standard deviation in 1988 is decently bigger by at least 3/10 of about a quarter. Let's say about a quarter of a square foot. So let's put all that into some text here. So they have approximately the same square footage of space in the mornings. However, 1988 did go down by 0.12 square feet on average. The standard deviation was lower in 1987 by 0.2212 square feet, meaning that in 1988, meaning that 1988 had more variation in the data. Okay. So we compared them. So let's not put this in red. Red's kind of aggressive. This isn't a note. This is an answer. Let's put it in. Let's do blue. Blue looks good. Let's see. I'm just checking. Okay. Yeah. Okay. Sounds good. So there. We did our description. We compared the data. We said they were similar. Then we talked about standard deviation and how that meant 1988 had more variation. So we're good. Short, simple, to the point. That's how we want to be. But notice I do have context. I keep reading answers on homework that provides no context. I need context. So don't just say, oh, they're similar. Oh, they're different. How? How? Tell me how. So give me the context. Okay, I need to get rid of all this space here. There we go. Number 9. Says the data in the table at right are the changes in the amount of space available to standing passengers at 19 stops between 1987 and 1988. In the table below, summary information is presented for this data. So they give us a bunch of summary information. This is still dealing with our scenario that was posed on number 8. So we're still dealing with the same info. And if you doubt me, if you really want to doubt me, then look back at the other data and look at the changes. And you'll see, oh, this is the same info. Yeah, it is. Okay, A. A asks us to use the raw data and summary information presented in the tables and construct box plots to compare the changes in available space in morning and afternoon. Reminder, don't forget to check for outliers. So based on just that reminder, this tells us we need to do a modified box plot. We need to do a box plot that marks the outliers. Okay, so let's see here. Which means to do outliers, we need to get our IQR. So let's figure that out for each of these. Let's do it up here by the table. The IQR, upper quartile minus lower quartile. So that means for this first one, it's going to be 1.3. Second one will be 1.8. Okay, now here's where the outliers come in. So let's focus on AM first. Let's do the most extreme outlier, the extreme one. So that's going to be our Q1 minus 3 times the IQR. So Q1 for AM is negative 0.9 minus 3 times 1.3. This gives us negative 4.8. Then let's do the mild, so minus 1.5 IQR. So negative 0.9 minus 1.5 times 1.3. This is going to give us negative 2.85. So those are the outliers on the low end. Then I need to get the high end. So Q3 plus 1.5 IQR. Q3 for AM is 0.4. So 0.4 plus 1.5 times 1.3. It's going to give us a 2.35. And then Q3 plus 3 IQR. It's going to be 0.4 plus 3 times 1.3. That's going to give us a 4.3. So on this, let's remember what this means. If it's below negative 4.8, we're extreme. If it's above 4.3, we're extreme. If it's between these, we're mild. Between these, we're mild. If it's between these, we're just normal. So let's look and see, is there any below negative 4.8 for AM? No. Is there any below negative 2.85 for AM? Looking for negative 2.85 or less. I've got some at negative 3. So this is going to be mild. This is going to be mild. Okay. Now, let's look for above 4.3. 4.6, this is extreme. That's it, okay. Now between 2.35 and 4.3 is mild. So 2.35 or higher. There's a positive 3, that's going to be mild. Okay, so it looks like we have labeled our values. So once we have our outliers, we can kind of go back and label what's our max, what's the min. So this extreme one has to be our max. And then negative 3, these would be the mins. So the outliers also help us identify those, max and min. Okay, so now I do a similar thing for PM, similar process. I'm not going to show that process. So if you don't want to just have the answers, boom, appear on the screen, I suggest you pause the video and try it yourself. Okay, so I have done the same process for PM. I've got 2 mild outliers, 2 extreme outliers. And I didn't show the equations again because I went into detail on the AM. So just do the similar thing for PM using 1.8 as your IQR, and you'll get the same values that I got. Okay, so we've done all the grunt work, but we still haven't even answered the question yet. We still haven't made a comparative dot plot. So let's do that. First thing we need to insert is our scale. So let's insert a scale. Okay. Now, I'm going to mark these in intervals of -5. So I'm going to count by 5s here. And I'm going to start, really, I'm going to kind of like start it. I'm going to do my first mark at -5. So let's say that this is, wrong color. Wrong color, wrong color, wrong color. So here's -5, 0, 5, 10, 15. Now let's space those out some more. Let's try spacing them out like this, see if this will work. There's -5, there's 0, 5, 10, 15. I bet we can even go further. In all honesty. Okay, so here's our scale. -5, 0, 5, 10, 15, and 20. So these represent the changes in space. Okay. So now let's do our actual plotting of the data. There we go. Okay. Now AM first will be done up here. So I'm going to do AM up here and then PM. So before we even graph that, let's do a quick 5-number summary. That way I can kind of know what I'm doing. So for AM, my min will be -3. So min, Q1, median, Q3, and max. So for AM, the min is -3, the max is 4.6. Q1 is -0.9. Median is -0.3. And upper quartile is 0.4. Okay, so let's use those numbers to get our box in there. That's the first step. We got to get a box. Get our box. Okay, so then let's see here. I need -0.9. So I need that Q1 to go right there. I'm just making marks so that way I can draw my box here in a second. Q3 is at 0.4. And then my median is at -0.3. Okay, so there's where my box is going to go. Okay, now let me draw my median in there. Hang on. Okay, so there's that part of the box. There's our box actually in there. Now, I need to go and draw my line out until I get an outlier, until I get to where my mild outliers start at. So my mild outliers start at negative 2.85. That's going to be about here. I'm going to draw a line to that point, and then on the other end of the spectrum at 2.35. So I need to draw lines out to those points. Okay, let's see. There we go. So there's that one. Now, I'm still not done though. I've got really three outliers to plot. So I'm going to put a mild outlier at -3. So at -3, I need a mild outlier. Which, remember, our mild outliers are done with open circles. So I'm going to come out here to -3 and do an open circle. Okay. Then I need a mild outlier at +3. What? Sorry, mild outliers are closed circles. My bad. I got them backwards. Closed circle. And then at +3, I need a closed circle. Extreme outliers are the open circles. So then at 4.6 for AM, I need an open circle. Okay, so there's my AM plot. Now I need to do the same thing, except do it for PM. So since y'all have seen the process for AM, I'm going to pause the recording and draw it. I want you to pause the video and draw it because it's just going to appear. Okay, so there's our complete dot plot. We've got AM in there, we've got PM in there. We've shown outliers on there. There's the complete dot, not dot plot, box plot. What am I thinking? There's our complete box plot. Okay, part B. It says the transit system is interested in understanding if their efforts to improve the standing space were successful. Remember, more space is better. Their engineers have suggested that the changes in the system would, on average, be more successful at increasing the available space in the morning than in the afternoon. Does this data support this initial belief? What specific of the plot in part A support your answer? Let's look at our plot in part A. Okay, let's see here. Well, if we look at the plot from part A, did it really improve much? I mean, for one, it says that suggested that changes in the system would be more accessible at increasing the space in the morning than in the afternoon. In the morning, we actually decreased the space more than what we did in the afternoon. So we're not only did it not work better in the morning, it actually was worse in the morning than in the afternoon. So let's put that into a paragraph that would explain our answer. So the available space as measured by the medians decreased. I want to emphasize that, decreased by 0.3 square feet in the morning and decreased by 0.2 square feet in the afternoon. This contradicts the initial belief of the engineers that the morning would show a bigger increase in available space than in the afternoon. So not only did it not increase the space, so not only did it decrease, the morning decreased more than the afternoon. Totally going against everything they were trying to do. This was a bust by all means of the word bust. They didn't get more space, they got less space, and even less space in the morning. Wow, so much for helping. Okay. Part C says, using your box plots in Part A, write a short paragraph describing the success the transit system had in increasing available space per passenger. Note any differences in success between the morning rush and the afternoon rush. Well, we've already kind of talked about this the whole time. There wasn't much success. So, yeah, let's again put that in paragraph form. There wasn't really much success. This was a bust overall. Now, some stations did see success, and we'll talk about those. I mean, if you look, some of these stations on average did see some success, but about half saw success, half saw failure. So overall, it was kind of just a whole wash. Let's talk about it. So according to the plots in both the morning and afternoon, the space available per person has actually decreased overall. This is indicated by the negative medians. AM is negative 0.3, PM is negative 0.2 for both of the distributions. There were some stations where the space available increased. So if we look above 6 stations for the AM and 8 for the PM, but overall there seems to be less space available during both of the time periods. Okay. So yeah, this wasn't a very good experiment, was it? They didn't do so hot. But that's okay. You live and you learn. So that answered number 9. Now we got to go on to number 10, which is still going off of the same thing. So the MTA guidelines in 1987 specified a minimum of 3 square feet per standing passenger. The engineers would like to report standardized measures, or z-scores, of this target value. That is, for each year and time of day, they will report how far away from the target value of 3 feet is relative to the distributions. So we're going to consider the original passenger space data for the morning rush in 1987. What are the mean and standard deviation for the sample? Well, part A, we're just going up and getting what we actually already computed. It's asking us for Morning Rush in 1987. Morning Rush in 1987. This is already computed, so per 8A, we said that X, let's see, what was X bar in 8A? For 1987, X bar was 3.24 square feet. So let's put that down here. 3.24 square feet. And then the standard deviation was 1.4964 square feet. 1.4964 square feet. Okay, we got that from 8A. And again, this is per standing passenger. Per standing passenger. Per standing passenger. How many standard deviations above or below the mean is the target value of 3 feet for this distribution? So what this means is that we need to get the z-score. The z-score. So we're going to use our value that we found. Our values that we found, and then the 3 feet. So we're going to say 3 minus X bar, which is 3.24, divided by 1.4964. So if we do that computation, we're going to get negative 0.1604. Okay. Okay, so now we've done our calculation. Let's type our conclusion, if you will, for this part. So we found the z-score is negative 0.1604. We can say, therefore, the target value of 3 feet is 0.1604 standard deviations below the mean. Okay, there's that one. Part C. The engineers would also like to provide descriptive information about the variability for reports to the public. They would like to make statements in something like the following form. So there's 2 different options that they want to make statements in the form of. either saying approximately blank percent of the passenger space value will be between negative 3s, which remember S is the standard deviation, and positive 3s. Or they want to say at least blank percent of the passenger values will be between negative 3s and positive 3s. Again, using the morning rush numbers for 1987, and based on your work so far, would you recommend using the empirical rule or Chebyshev's rule to establish this percentage? Explain your reasoning in a few sentences. Okay, so let's see, we have to pick between empirical or Chebyshev's. Let's remember the difference. So Chebyshev's is the second one. This is going to be Chebyshev's. Or do we want to use empirical? Well, what do we have to have for empirical? Empirical, we have to have a symmetric distribution. So needs to be symmetric. For Chebyshev's, it can be any shape. So what we're going to have to do is use the morning rush numbers for 1987 and see, okay, what would our data look like? Okay, let's scroll up. So we want to use the morning 1987. One thing we can do to determine the shape is to make a histogram. That'd be the easiest thing to do. Make a histogram and use the minutes, or sorry, the square feet as your buckets. So how many are between 1 and 2? How many are between 3 and 4? 4 and 5, 5 and 6, 6 and 7, etc. That would be the easiest option. Because remember, histograms, as we learned in chapter 3, show us the overall shape of the data. They give us a brief insight into the data. So let's start by saying that. I know I'm doing a lot of scrolling here. Let's start by saying that. So first, we need to understand the shape of our distribution for the morning rush number, morning rush in 1987. Let's create a histogram to look at this. Okay, so now we need to make a histogram. So first thing you want to do, insert your axes. Okay, so there's our axes. Now down here we want to do square feet of space. And I'm going to start here at 1 square foot. And then I'm going to end up counting all the way up to 7. That way I can make my bins for my histogram. So 1, 2, 3, 4, 5. And you know what? Let's space these out a little bit more. Okay. 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7. And then up here on the y-axis, let's do just plain frequency. We want to make it easy. Let's not do relative frequency, just do plain Jane frequency. And let's see, which one is the most popular? We need to scroll back up to the data to see. All threes, bunch of 2. The number I'm saying most common is 2. So how many 2s do we see? 1, 2, 3, 4, 5, 6, 7, 8, 9 2s. So I probably need to at least go up to 9. At least go up to 9 here. Let's count by 2s. 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. I'm going to put small marks in between. That way we know that's the ones. Okay, so from 1 to 2, how many observations were there? From 1 to 2. Let's see, 1, 2. So I need to come down here on my histogram and draw a box that only goes up to 2. Insert shape, rectangle. Okay, there's that one. Now 2 to 3, we said 9, but let's go count and double check. 2 to 3. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so I need a box that goes up to 9 now. Okay, now let's check between 3 and 4. 1, 2. 1's exactly at 4.0. So remember that you can't count it into the 3 box. That's got to go into the next set. So we're just looking for 3s right now. 1, 2, 3, 4, Okay, 4. So let's draw a box at 4. So from 3 to 4, we're going to be at 4. Okay, now 4 to 5. Whoa, I went way too far. 4 to 5. 1, 2. I only see 2 from 4 to 5. So insert shape. Let's do 2. Uh, 5 to 6. None from 5 to 6. 6 to 7. 1, 2, and that's it. So, okay, let's draw our 6 to 7 box, and then we'll be done with our histogram. Then we can analyze it. Okay, so if we look at this histogram, is it symmetric? No, not nearly. This histogram is not in any way, shape, or form symmetric. So, hang on here. Let me do something. Let's put that down here. Come on. Since our data is not symmetric by nature, we're going to even say, in fact, it is right skewed. We would want to use Chebyshev's rule to establish this percentage. Okay, and then now that we've said that, let's actually use Chebyshev's rule. So in your recommended procedure from Part C, what percentage should be used to fill in the blank in the appropriate statement? So for Chebyshev's, That's the one that says you have to do 100 times 1 minus 1 over k squared percent. Now the k in our case is 3. So this is going to be 100 times 1 minus 1 over 3 squared percent, which is approximately 89%. That means in our statement, we can come in here and say that, let's just set this up, using Chebyshev's rule, the statement should say at least 89% of the passenger space values will be between negative 3s and 3s. Okay. Now, of course, if you were doing this for a paper, for a legitimate report, you wouldn't use S's here. You would actually calculate negative 3 times S and fill that value in. 3 times S, fill that value in. So if we did that, what is negative 3 times the S we found? S was 1.4964 times 3. So negative 4.84, or sorry, essentially 4.5 to positive 4.5. That's what you would put in for the S's. 3S is 4.4892, which is 4.5, essentially. So anyways, now let's have a different type of problem. We're done with this transit type of problem. Let's move on. Finally, transit is behind us. Found a z-score that corresponds to a utility bill of $60. What does this score tell you? Well, they tell us the mean and the standard deviation. So let's calculate the z out here. We'd say 60 minus 70 divided by 8. This would get us negative 1.25. Now, with that negative 1.25, we can use the empirical rule here. What is that close to? If we think of our empirical rule, well, we know half of the data would be a z-score of 0. We're below 0. What's between 0 and negative 1? What percent of the data? 34%. So I don't really have much room here on this problem, but let's try to sketch. That way we can visualize this. So here's the mean. Here's the mean, X bar. Then we've got 1s, 2s, 3s, negative 1s, negative 2s, negative 3s. So between each of these, if I drew, the empirical rule says that 68% is within here. Well, what's half of 68%? 34%. So 34% is in each half here. Now, I'm at negative 1.25. So my value is actually kind of like right here. Well, I can safely say that, well, up here, this is half. That's half. So 50% plus 34% is about 84, at least 84% using the empirical rule. So let's see what I can fit in here. So the utility bill is 1.25 standard deviations below the mean. So a utility bill of $60 is cheaper than at least 84% of the customers. Okay. Now we need to find the z-score that corresponds to a utility bill of $71. So let's do that. Kind of squeeze it in down here. Z equals 71 minus 70 divided by 8. That's going to be 0.125. If we calculate it, because it's 1/8. 71 minus 70 is 1. 1 over 8 is 0.125. Well, that's going to be on the positive side of our graph up here. That's going to probably be really, really close to here. So this one is where A's at. This one's where B is at. So we can say that we can kind of mirror, honestly, what we said in A. The utility bill is 0.125 standard deviations below, no, not below, above the mean. So a utility bill of $71 is cheaper than approximately, I can't say at least because it's not at least, it's really close to about half, 50% of the customers. Okay, so then it asks, part C, it asks us to kind of put these two together. Which bill is more likely, the $60 bill or the $71 bill? Well, we have to ask ourselves, which one is closer to a z-score of 0? The $71 bill, which means that one is more likely. If it's closer to a z-score of 0, then it is more likely. So the $71 bill, $71 utility bill, is more likely due to the z-score being closer to 0. And that's it. How can you tell? That's how you can tell. Okay, so I know this review was super long. There were lots of computations, but this is an important chapter. We're going to use this concepts in this chapter for the rest of the course. So it's really important that you understand it, you know it, and you internalize it. So with that being said, study, email me with any questions, and good luck on the test tomorrow.